Welcome back, everybody. We are looking at the bottom of page 55, and in this video we're just going to summarize a few new derivative formulas that we're going to add to our list of formulas that we already have. And we'll start with the one that we just derived in the previous video. So the derivative of natural log of x, we went through a derivation and came up with a formula of 1 over x for that. Okay, we use the idea of an inverse function, the fact that the natural log function is the inverse of the exponential function. Okay, and the remainder of these formulas, we're just going to fill in, and I'm going to make the comment that we could derive the rest of these three formulas using a similar method to the one that we used to come up with the formula for the natural log. We'll skip over the derivation part, though. Okay, so for example, the formula for the derivative of the arcsine function is 1 over the square root of 1 minus x squared. And if you're wondering what is the arcsine function, okay, if you haven't heard of it before, that's just the name for the inverse of the sine function. Okay, and same over here, arctangent is that's the notation for the inverse of the tangent function, and it has a derivative that looks like 1 over 1 plus x squared. Okay, again, we could derive those two formulas, but we're going to skip the details of that. Okay, and then just for the sake of completion, even though this formula up here doesn't come up very often, I'm going to fill it in. So if you wanted to take the derivative of log base a of x, it actually looks like 1 over x ln of a. We probably won't use that formula again this semester, okay, but there it is in case it comes up, okay, where a is a constant. Okay, and then looking at the box down at the bottom here, summary of derivatives involving exponents, this is going to be review from earlier in the course. Okay, so if a is a constant, let's first look at how we would take the derivative of x to the a. Think back for a minute. Note, the thing that I would emphasize here is that x is a variable and a is a constant, so we're raising x to a constant power. How do you take a derivative in that situation? Well, you might recognize that as just being the power rule, ax to the a minus 1. Okay, if you've got x raised to a constant power, you just bring the power down, subtract 1 from the power. That was one of the first derivative formulas that we talked about this semester. Okay, what if it's the other way around? Okay, if you take the derivative of a raised to the x, where the base is constant and the exponent is variable. Okay, well, that one was our formula for the derivative of an exponential function that looked like a to the x ln of a. Okay, and this last formula, we are actually going to skip over this semester, but there is a formula for taking the derivative of a function raised to a function where the base and the exponent are both variable. Instead of writing down a formula, though, there's generally a special technique that you could develop to do this. Okay, so like I say, we are not going to cover this specifically this semester, but if you're interested in looking at that on your own, you're welcome to take a look at my written solutions to example 3C and D down here, okay, on the next page. Okay, again, you're not required to do that. We will not be covering that, but if you're interested, feel free to look at it on your own.